Good morning, friends. Uh, Today we are going to design a CMOS inverter using 65 nanometer technology. This is the first practical of your subject VLSI design and technology. The aim of this practical is to design, prepare, and simulate the layout of CMOS logic inverter using the MOSFETs. Okay, and for this purpose, we are going to select a foundry of 65 nanometer. Means we are going to use the 65 nanometer technology. And another way, you can also use the 120 nanometer or 45 nanometer technology to compare the results. Along with this, you have to apply the capacitive load of 0.001 picofarad. This is the aim of our first practical. Now, what are the learning objective of this practical? The learning objective of this practical is to design and verify layout of CMOS inverter for specific technology, means 65 nanometer and 129 nanometer for the capacitive load 0.001 picofarad. The second learning objective is to understand the microin software, is how to use the microin software for development of layout of CMOS circuit. And third is our ultimate aim is means observations are to calculate rise time and fall time, power consumption and area which is occupied by CMOS logic inverter. Okay, clear? And what is the objective of this practical? After performing this practical, you are able to design and verify the layout of CMOS inverter for that specific technology. The requirement of this practical is you will require one desktop or laptop and which is equipped with microwin software. Okay. Now what is meant by CMOS inverter? CMOS inverter is basically most important logical cells in circuit design. And how it works? Now, this cell consists of pull-up network and pull-down network because CMOS is complementary metal oxide semiconductor device. It consists of two networks, pull-up and pull-down network. In pull-up network, we are going to use the PMOS, means P-channel MOSFETs, and in pull-down network, we are going to use the N-channel MOSFETs. Now, whenever we are going to apply the logic 0 or logic 1, it will invert whatever they applied at the input. Okay, hence it's known as the inverter. Means let's see. This is the symbol of CMOS inverter. Okay. Now, and second, you have shown the truth table of the inverter. Means whenever we are going to apply the logic 0, output is logic 1. Whenever we are going to apply the logic 1, output is logic 0. Okay. Okay. Here you can see whenever you are going to apply the logic 1, at that time P channel MOSFETs is switch off. Means it does not conduct any current, and N-channel MOSFET switch on. When it switch on, at that time output is connected to the ground. Means output is always connected to the low impedance connection. Hence when logic 1 is applied, output is connected to the ground, means output is 0. Okay, and whenever you are going to apply the logic 0, at that time N-channel MOSFET is in off condition and P-channel MOSFET is in the on condition, and your output is pull up towards the VDD. Means output is 1. This is the basically working of CMOS inverter. Okay. Now these are the CMOS transfer characteristics. Means the characteristics which are drawn by applying the input and observing the output. Okay. Now these characteristics are divided into the 1, 2, 3, 4, 5 regions. Total 5, A, B, C, D, E. In A region, you can see whenever the input applied is logic 0, and it will gradually increasing to the logic 1. Means whenever you are going to apply the logic 0, at that time N-channel MOSFET is off conditions and P-channel MOSFET operates in the linear region. Okay, in B region, N-channel MOSFETs operate in the saturation region and P-channel operates in the linear. And at C, whenever the gradual decreasing means at sudden decreasing of voltage, when input voltage is increasing towards the VDD. At that time, what happens? Both the transistors operate in the saturation region. And then D region, N-channel MOSFETs operate in the linear region and P-channel MOSFET. And finally, whenever my input applied is logic 1, at that time my output is logic 0. Means N-channel becomes or operates in the linear region and P-channel operates in the off condition. Okay. Okay, now let's see how to design this CMOS inverter. For that purpose, first of all, you have to open the microwind software. Now I will open the microwind software. One minute. Okay, we have microwind 3.1 version full. Then select the system, and in system you can see microwind 3.1.exe file. Double click on that file. Okay, now here you can see on right hand side you can see the palette. From palette you have to select the material. Okay, now first of all, before going to select the material, whatever the this black screen is nothing but by default it is known as a P well. Okay, means whenever you are going to draw the n channel MOSFET device, there is no need to design the another P well. This background means this is a you have provided the P well as itself. Okay, now as we know that CMOS inverter consists of P channel MOSFETs and N channel MOSFETs. Okay, now at in pull-up network you have to design a P channel MOSFET. For that purpose you have to draw the N well, because P channel MOSFET is always drawn in the N well. Okay, now means while before going to start the device you have to understand what are the here in palette you have not provided the P well because it is a background, add background, or you have to draw the layout in itself in the P well. Okay, then after that second device is a N plus diffusion, then third is the P plus diffusion, then polysilicon material for gate region, and then metal 1, metal 2, metal 3 for multi-layer device. Now here we are using the metal one. Then to connect the two different materials you have to put up the contact. Okay, now starting with first of all select the file, then in file select the foundry. In foundry here you can see CMOS 65N means rule file. This rule file is nothing but the technology file. Select the CMOS 65N rule file and open. After opening this, here you can see the scale 5 lambda means the distance between two dots is 5 lambda, and this distance is actually in micrometer is 0.175 micrometer for 65 nanometer device. Now to draw the P channel MOSFET, first of all here you can see the basic diagram. Okay, this is the P channel MOSFET, and P channel MOSFET is always drawn in the N well. Okay, now start with this, draw the N well. Okay, while drawing this you have to satisfy the rules of technology. Okay, these are nothing but the lambda rules. Now here you can see to check the rules here DRC is given. Okay, DRC. But first of all, while drawing the layout you have to remember the minimum size of the N well or P well, minimum size of the polysilicon material means width of the polysilicon material, the minimum width of the metallic layer, then minimum distance between the metal and polysilicon layer, minimum distance between the polysilicon yeah, P well, N well and N plus diffusion. Okay, these all rules you have to satisfy, and to remember all these rules here you can in help design rules you have given. Here you can see the rules. Okay, start with the polysilicon. Polysilicon width is 2 lambda and the distance between two polysilicon is 3 lambda. The metal width is 3 lambda, distance between two metal is 4 lambda. Then again here you can see the 1 minute. Okay, contact width should be 2 lambda, distance between two contact is 4 lambda. N diffusion material width should be 4 lambda and spacing between the two N diffusion material is 4 lambda. In this way, first of all, you have to remember all these well, and for N well, you can show the width should be minimum 10 lambda and here spacing should be 11 lambda. Similar for diffusion P, width should be 4 lambda and between two diffusion material spacing should be 4 lambda. This all rule you have to remember before drawing this. Okay. Now this is a n well. Here you can see the distance between two spot is a here 5 lambda, means 5, 10, 15, 20, and near about 22. This is the means length is 22 and width is near about 20. Okay. Now I will draw again. This is a gun which is used to delete the device. Okay. Now select the anvil. Okay, this is the anvil, and in anvil to draw the P plus device you have to put up the P plus diffusion material. Okay, now after one I will check the DRC if it violates any conditions. Then for n channel device, P well is by default given here. Hence no need to draw the P well. And in P well you have to draw the n plus diffusion material. Okay, then again check the DRC. After that put the polysilicon. Okay, now I will drag this using the stretch and move tool. Okay, here you can check again the DRC. Okay, now everything is fine. After that we have to connect this P channel device to the VDD, means source of the P channel device to the VDD and source of the N channel device to the ground, and from drain we are taking the output. Okay, then select the metal one. Again select the metal one. Okay, then put the contact here. Now which contact you have to select? From we are going to connect P and metal and P plus contact. Okay, this is the contact P plus diffusion material to metal one. Okay, I will put this contact here. Again at downward side N plus diffusion material and metal. Then this is here contact N plus diffusion to metal. Put this contact. Okay, now connect the VDD. Here you have to select the VDD supply to connect the P channel devices source to the VDD, and ground. Second, connect the source of N channel device to the ground. Okay, after that you have to short the drain and take the output. Okay, again put the contact, upper side P plus contact, lower side N plus. Okay, again I will check the DRC. Okay, now here now you have to apply the input. Okay, how to apply the input? Here you can apply the pulse, either 0 logic 1, or you can apply the train of pulses through a clock. Here I will apply the train of pulses to the clock. This is input. Okay, here for multiple input you can change the rise time and fall time also, assign. And for observing the output, visible node you have to put here. Okay, now save the device, save the design. After that, here you have option the simulate, run simulation. Okay, in the run simulation you will give the one warning. That warning is NVL region is floating, means floating NVL can damage either the chip or software. Now why it is important? Why you have to connect the, now here this NVL device is floating. This warning shows that here you have to apply the supply, means you have to complete the circuit. Hence to complete the circuit you have to apply the VDD to the NVL also. Okay, and now circuit is completed. Okay, again save the device and run the simulation. Okay, now I will minimize the time scale to visible properly. Okay, again minimum or maximum frequency to observe reset. Okay, now here you can see this is the input logic 1. or logic 1 your output is logic 0, and for logic 0 your output is logic 1. Now means whatever the circuit you have designed, it will act as a CMOS inverter. Now to make to note down the observation reading, now here you have to note down the rise time and fall time. Now what is the definition of rise time? So time required by the waveform to rise from 10 to 90% of its final value. Okay, now this rise time here in software is automatically calculated, and this rise time here you can observe this is the 0.197 0.197 nanosecond, near about zero point 0.2 nanosecond is the rise time. Similarly fall time is very small. The fall time is when the waveform goes from logic 1 to logic 0. Okay, means it goes from 90% of its final value to the 10% of its final value. Means it is a 7 picosecond. Means these are your two readings. For 65 nanometer, rise time is 0.2 nanosecond, means 0.197 nanosecond, and fall time is 7 picosecond. Okay, okay. Means here you can take a constant value. Means here constant value is zero point 0.2 nanosecond and 6 picosecond also. Okay, this is first reading, rise time and fall time. Second reading is power consumption. Power consumption, here you can say your power consumption is automatically calculated. P is equal to 0.661 microwatt. Clear? Okay. Now this reading, but our aim, what we have said, we have to take the reading by assuming the capacitive load 0.001 picofarad. Now this part is remaining. Hence again what we do, we will select the palette. In palette here you can see the add virtual capacitance and connect the virtual capacitance here at the load. Okay, and value is 0.001 picofarad. Okay, okay, 0.001. Okay, that value is 0.001. Clear? Okay, again save this, and now you can see the change in load capacitance. Whatever the, as the load capacitance is increased, here you can observe that my rise time is near about same 5 nanosecond. Again reset. Okay, my rise time remains same 0.200 nanosecond, but my fall time now increases. Okay, okay, my fall time is now 17 picosecond. Okay, in my fall time also increases because of this load capacitance. Means it will take more time to switch from logic 1 to logic 0. Okay, clear? In this way you have to see the effect of adding the load capacitance also. Okay, now again my power is increases. Power is 2.617 mag, means it near about constant, somewhat increases. P is equal to 2.617 microwatt. This is the secondary. Means now rise time 0.200 nanosecond, fall time 17 picosecond, power is 2.617 microwatt. Now third reading we have to take area. Select the analysis. Okay, in analysis measure distance. Okay, the means now scale is selected. Now you have to select the whole design. Means you have to select the, okay, we have to delete this first of all. Okay, I will again select the measure distance. Okay, select the measure distance, and from here you can, oh sorry, undo. Okay. In analysis, select the measure distance again. Okay. Now the scale is selected. Now I will join your device. Okay. Here you can see the width is 0 to 1, width is 1.61 micrometer and length is 1.925 micrometer. Means to calculate the area, multiply this 1.61 into 1.92. Okay, I will open the calculator. In 1.61 into 1.95. 1.61 1.61 into 1.925. Okay, means area is 3.099, means 3.1 micrometer square. This is the area of your layer. Okay, and this is our first practical. In first practical, you learn about how to design a CMOS inverter using 65 nanometer technology, assuming the load capacitance 0.001 micron. Similarly, you have to design the CMOS inverter for 120 nanometer technology, and finally you have to put the reading in this practical and in this observation table and compare the result for two different capacitive load. Means for 65 nanometer you have to take the two reading. For first reading is 0.001 picofarad and second reading 0.001 picofarad, means increase decreasing the load capacitors. Okay, now here I can also show you how to decrease the load. Only select this value, double array, control U. Okay, I will again delete this. Mm, 1 minute. I can delete all these. I will repeat the process. Now I will increase the value of capacity. Decrease the value of capacitance 0.0001 triple 01. Okay, and now after connecting VDD and ground, I will simulate the circuit. Okay, save the device, simulate it. Okay, by decreasing the value of capacitance, my fall time is also decreased and rise time near about constant. Okay, now again power is decreased 0.863 microwatt. In this way, this first practical is completed, and here what is our conclusion? The CMOS logic inverter circuit we have designed using the MOSFETs by for two different technologies and assuming the two different load capacitance, and this layout of the CMOS we have simulated and verified for that particular technology. Okay. Thank you.